LinkedIn always takes a bit longer than YouTube. There we go. Excellent. All right. So almost right on time. Wouter, very, very excited to have you on a deep dive. I know we've been knowing each other for 5, 6, maybe 7 years
Yes,
already. So it's been a
definitely.
pleasure talking to you over the time, see how you progressed and how the company has been doing. Today we'll talk about optimizing the Porsche Taycan. You brought a little anecdote and a little car model with you today, and we want to talk a little bit about the topic of shape morphing and next-gen aerodynamics. So I'll hand it over to you. So Wouter, the stage is yours.
Yeah, yeah. Likewise, it's been great to see you progress as well with Apex Marketing. So really cool and impressive work. Yes. So the long story short about how it all got started with AirShaper is that I had too much free time, and as a kid, I always wanted to design cars. So I created this car, which was based on a principle with internal and external air channels to generate lateral forces on the car to go faster through the corners instead of just using downforce, which makes you dependent on the friction, lowers your ride height as you speed up, and so on. Um, and then I played around with some manual design of a framework that I would then 3D print for the chassis. And I didn't know how to run aerodynamic simulations, so I contacted a design agency here in Belgium where I live, and I asked them, "Can you run a simulation for me?" They said, "Yeah, we can, but that will cost you 3,000 euros for one single simulation, which is a market a conform rate, but it's a lot, especially for a hobby." So I said, "No, thanks." But then I quit my job, went traveling for a few months, and when I came back, I actually needed a job, and I just applied at that engineering agency that made me the offer. And then we started working on this concept, and I also started working on customer projects, which was really cool. Did that for 6 years, CFD simulations, wind tunnel testing, NASCAR, IndyCar, drones, and so on. After I had done 5 years before on structural simulations. And then after 11 years of doing simulations, I thought, well, this is actually prohibitively expensive and difficult for customers to get into this. Um, so instead of using the traditional approach, which is to use a license, which is 50 to 100,000 euros, expensive hardware, an expensive person to operate the software, we wanted to flip things around with AirShaper and just say, well, just pay per simulation or pay for a number of simulations without the investment in knowledge, hardware, software, and so on. And that's how AirShaper came to be.
Yeah, that's super exciting. Wouter, I think if you want, you can show us a little bit about the topic of shape morphing and shape optimization, and then we can delve straight into the software, I'd say.
Yeah, happy to. I'll share my screen here. Just a sec. Share screen. Can you see my screen?
Yes.
Okay, fantastic. So I can't show too many details on a real customer projects, but this is a generic example. People in the automotive industry probably recognize this shape. This is what they call the Ahmed body, which is a very, very, very simple car model which they once devised to run benchmark wind tunnel tests and simulations to just check how well do CFD results correlate with wind tunnel test data and so on. And then we actually made it super accessible to run what they call adjoint shape optimization. Now, that's a very technical term. Basically, what it does is after running a normal aerodynamic simulation, the software will run a second simulation, which is called a dual or a adjoint simulation, which somehow is an inverse calculation which links your target function, your goal function, which in this case is to reduce drag, to the geometry that you have. So for every single point on the surface, it's as if you would just move that point outward or inward, a small dent or a small bump on the surface, rerun the entire simulation, and then check did my drag go up or down. And then you do this for every point on the surface, and then you get what they call a sensitivity map, which is a color-coded map that indicates how should I morph the shape. But then we go one step further, and we actually have our software implement this advice. So it starts to morph it, checks it again, morphs it again, checks it again, goes through a number of cycles, and then actually ends up with an improved shape. And the cool thing is that in terms of regions, you can just move this region around. The goal is that you position this on a critical area. For example, if you say, I have a car and I want to optimize the headlights, then you would just bring this area forward. You can rotate this, position it, scale it however you want. to put it around the area that you want to optimize. You can do multiple areas at the same time. And once this is finished, you'll get the result for the optimization. So if I load the videos here, so it's quite heavy. So we post-process this into videos. We optimize the rear of this Ahmed body. And at the rear, you have what they call the downward slope or the slant angle. For this Ahmed body, you have different versions there. And what the software is doing, it's automatically creating what they call a ducktail spoiler on this car, which is really interesting because that's exactly what Porsche has on their Taycan. Only in this case, we didn't tell the software what a spoiler is. It doesn't know what a spoiler is. It's just mathematically looking at a better solution to reduce drag, and it just comes up with this shape. And so technically, what it's doing is it's creating a bit of back pressure here, which then translates in a reduced under pressure on the slant angle, which reduces the drag effect that you have on the back of this Ahmed body, this very simplified car. And we've applied this to many cases. If you go to our list of sample cases, you also see that we applied this to winglets, which are a very critical part of the wing, which is the end of the wing. For example, there you can see that if you apply an optimization, it just comes up with these very natural, organic looking shapes, which in some cases, actually mimic what you see on real cars, or in this case, what you see on real birds, for example, like what you would see at the end of a real wing. In this case, this increased the lift by over 50%. So that's really powerful. And we also have, I'm going to scroll through some projects here. We also have a version of this where we analyze a car and then we can just ask for this advice function without actually having to go through the morphing. So we can offer it at a lower rate, and then we just get this color map. So the colors that you see here on the surface are just a hint for the designer. Well, in this case, if you want to improve downforce, well, then you should move the surface inward where it's blue, should move it outward where it's red. And this sometimes yields very interesting results. For example, on this rear wing of the car, if you want more downforce, it's telling us to increase the height of this lip here at the end of the wing. This is the trailing edge of the second element of the rear wing, which is quite cool because in reality, what people do is they add like a small vertical flap there, which is what they call a gurney, which is really cool because the software is now telling us make a gurney, and it doesn't know what a gurney is. But there's also more complex suggestions. For example, this is the side plate of the rear wing. And the side plate actually prevents the high pressure air at the bottom of the wing. So if you look at the pressure, you'll see that you have, sorry, the high pressure air at the top of the wing to actually short circuit and go to the low pressure at the bottom here. That's typically your wingtip vortex. So you want to avoid that shortcut. That's why you just simply put a plate there and block it.
Mm.
So what the design advice is telling us, well, this is now a flat plate, but you might as well actually take the outer edge here, push that outward a little, which means the air flowing alongside the side will be kicked outward, which creates a low pressure at the rear. And this low pressure then acts on the back side of the wing, creating extra downforce. So it's like doing a change in like the horizontal plane to make it more effective in the vertical plane further away. So really cool how you can actually use mathematics to optimize designs.
It's pretty cool. One hint, Wouter, can you maybe close that little window on the right side? You can just click on the X, I believe.
Let's
Then
see.
people can see the full beauty of AirShaper, the UI.
Yes.
Perfect.
Okay, great.
Excellent.
So that's in a nutshell what we do with the automated optimizations. Now, if you want to look at just other cool applications like hypercars, for example, we got the OK to show this one. So this is a custom Lamborghini that we did. And if you want to see this one, just head over to our video page and you'll see it. I think it's page number 5 already by now. So this one has been built for real. I'll just turn off the volume, but this one has been built real life. It's been built, it's been tested, and it's actually been taken to the proving grounds. And they were aiming for 420 kilometers per hour, and they already hit 447.8 kilometers per hour on the first test, and we're still aiming to go faster. Now, the way we did this was to upload this car. I've got too many tabs open. Let me just go back to the right one. We just uploaded a 3D model of the car, which was a modified Lamborghini. So They took a 3D scan of the base car to get the hard points right, but then they kicked out all of the body panels, the underfloor, everything was completely redone except for the windscreen and the A pillar and the side windows. All of the other body panels, if I'm not mistaken, were done from scratch. And through numerous iterations, and also that morphing that we discussed, we were able to, together with the designer, or the designer was able to do this with AirShaper, to cut the drag compared to the base Lamborghini by 28%. Um, and that's crucial because if you're going for a top speed record, at those speeds, the energy that your engine is providing is all spent. 95% of that is spent, or let's say 80 to 90% is spent on pushing the air away. So if you can lower your drag by 28%, that gives you enough room to actually go faster again. And the designer was working with these models. So it's a complex combination of a 3D scan of a car. And that's really not the easiest model to get right in CFD simulations, because usually in most softwares, you have to close all the gaps and the holes in 3D files before you can even run a CFD simulation. We can just work directly with those. He combined a 3D scan with custom wheels he designed with surfacing elements, which are not even solids, surfacing elements which he then used to replicate or to visualize the body and the styling that he had in mind. We just uploaded it to AirShaper, or he did actually, and he just went through the basic setup procedure, which is to just say, well, it's moving, which means the ground will virtually be moving. He set the velocity. We even went to custom compressible simulations of 500 kilometers per hour. He set the angle of attack, the units, and then he added wheels to the simulation. Now, the cool thing is to avoid that, you have to spend lots of time finding the axis of the wheel, defining the radius, selecting all of the elements which are part of one wheel assembly, and so on. He just used our automated selection. So I just click one button and our software just detects the wheels and so on. So you don't have to do anything yourself. We detect the axis of rotation. We detect the radius, which means we can calculate the RPM based on the speed of the vehicle and so on. And behind the scenes, mathematically, we'll just translate this into boundary conditions, which mimic the rotation of the wheel. And that's it. And then afterwards, he got the results in his mailbox. So if you look at this, this is what we call the pressure clouds. This is an indication as to where you're losing energy. So typically you'll see that on this car you don't have too many areas left actually where you're losing energy, but you'll see that on the A pillar you still have quite a strong vortex. That's one of the parts that we weren't able to modify because that was the donor car. But other than that, almost everything was cleaned up. So if you look at the inside here, we have massive air curtains here. So you have airflow going to the inside, which is then being spat out on the sides, which helps to create a curtain across the wheels to lower the drag. We've got wheel arch ventilations here, so the high pressure air, which is building up in the wheel well, can evacuate via this slot here instead of being pushed outward where it disturbs the free airstream. We've got the inlets for the coolers here. We've got ventilation of the rear wheel arches, and then we spent so much time optimizing the diffuser. This was a really interesting area because we needed to tweak the spillover of the tires and make sure it didn't pollute the diffuser. This is actually not the final version. In the final version, we worked with a vertical wall here to further shield the wake of the wheel from the diffuser. And we optimized the front splitter quite dramatically. This is like an air dam, which is still present on the original car, which was later also removed on this car. And then we analyzed the pressure just to see how strong this vortex is affecting the airflow. We looked at the low pressure here to generate downforce at the front, at the rear. And the cool thing about this project is that we weren't necessarily looking for too much downforce, because your aerodynamic forces, they scale with the square of your velocity, which means that if you go from 200 kilometers per hour to 400 or even 440, they go up by a factor 4 and more. So this would actually completely squash the car against the ground. So we were looking for a moderate amount of downforce at 400 kilometers per hour. But what we were mainly interested in is to get a good aero balance. So we automatically calculate the front and the rear downforce. And in this earlier version of the car, we saw that we didn't have enough downforce at the rear. That's why I'm showing you this one, which is why we then applied morphing to these small wings that we had to increase the downforce at the rear. We could tweak the diffuser as well, and so on, to restore that aero balance, so you have a mild amount of downforce at both the front and the rear of the car. Any questions?
No, I think that makes sense about that. The question is, how do you balance the downforce and the basically the aerodynamic resistance, the drag? How do you balance that?
Yeah, so the main goal was to reduce the drag. If you don't reduce the drag, you're never able to achieve that top speed. Of course, you can compensate for this by adding more horsepower, but this one already has 1,900 horsepower, so there's a limit to what you can do without just burning up the car. So you can add more power, but there's limits to that. So reducing the drag is super important. Now, sometimes these go hand in hand. If you want to reduce the drag by cleaning up the underfloor and making it like one smooth surface, you also increase the speed and the attachment of the flow and the performance of the diffuser, which means you can also get more downforce. So sometimes you're lucky, and whatever you do for drag reduction still works for downforce generation, which was the case on this car. But
I
then you have
see.
to tweak it with dive planes and wings to actually balance it out.
Yeah. The question for the rear lift coefficient, how did you find the balance? Like, how do you decide on a perfect quote unquote number that's
Yeah,
acceptable?
so it depends. So for some projects, we do car design from scratch. And then you would have like a specification or a goal set by your customer. Like we want 200 kilograms of downforce at a certain velocity. Okay, then you can just aim for it. In other cases, like in this one, but like in other projects as well, we also work for Bertone, which is quite nice. It's also based on a Lamborghini. And there you want to design like a very unique car. If you just go to Bertone, to their website, this is a really nice car, the 110 that they designed. Um, so what you want to do there is to make sure that you don't make the aerodynamics worse. So in that case, what you can do, you can take the donor car, make a very precise 3D scan of the car, run the analysis on that car, and use that as a benchmark, and then say we want at least what this car has, and then you can take that as a reference, and then you can start to tweak it. If you say, well, but I want more top speed, okay, then let's focus on drag reduction. If you say, no, this one has to be track oriented, then let's focus on a bit more downforce and sacrifice some of the top speed. Those are the typical references that we use.
Makes sense.
Maybe another
Make
cool
sure to
example
close
if you
the
want.
mini
Yeah.
window. Make
Oh,
sure to
sorry.
close
Yeah.
the mini window again. Yeah.
Yes,
Super
it
annoying, I
popped
know.
up again. Okay, my apologies.
Yeah, I think no questions so far about that. Go ahead.
Okay, great. Yeah, we had a really fun one over the weekend, and also new for you, Jousef, because this is brand new. So Pikes Peak happened this weekend, and so Pikes Peak is I don't know if you know it, but quite a lot of race enthusiasts go there to see cars race up the hill. It's a hill climb competition, and the person who won it 4 times already is Robin Shute. And this year he was racing a modified Chevrolet Camaro of 1976. And you would say, well, that's pretty bad in terms of aerodynamics, and you'd be totally right. Now, the only thing is, they got to work heavily on the aerodynamics, and they just made a monster out of it in terms of performance. So, this is the real car. So, we got the approval to make this public, this simulation. So, after the call, if you want, you can share this link, and people can go check out this simulation. You can see that the nose of the car, they actually completely chopped it up, made it open, and so virtually, this is a nice curve of the front hood. Visually, it still looks like a Camaro because they have this bridge here. Um, they added a massive front wing, and that wing is in ground effect. So that means it's very close to the ground. So the air speed up at the bottom just creates a tremendous amount of downforce at the front, really pushing the front wheels onto the ground. They added side skirts, kind of like the McMurtry, to avoid or to create that extra low pressure area without airflow leaking in and reducing that low pressure effect. And then they added a massive diffuser. So you can see all of these blue areas. That means there's a tremendous amount of downforce, which they then even augmented by adding vortex generators, which means the flow passes alongside them, trips, which creates high speed vortices. And then these vortices that you see, they also create extra downforce. And this car in total has a lift to drag ratio, which is how much lift do you get for the same amount of drag on your car, of almost 4. That means for every Newton or kilogram, if you want to call it that way, of air resistance going forward, you have 4 kilograms of vertical downward push on this car, which is insane. And then combined with, in this case, 1400 horsepower, um, this results in a pretty cool car. So this one with the AirShaper stuff on it, I just raced over the weekend. It was really cool to see how it performed. Other examples, I opened up this one. Let me just go back here and select this. We have another example where we actually show how you can set up radiators. So radiators are quite important for cooling, but they also affect the aerodynamic drag. So we have the option to add radiators to the simulation, which means you can just provide their pressure drop data, which means how much pressure buildup do you get in function of the airflow or this airspeed through the radiators, which means afterwards you can just click on the radiators and you can analyze the flow rate through them. So this is another public example. This is an open source race car project, the Perrin 424. And the way it's set up is that the airflow enters the side pods here, and then it enters this chamber, let's say, and the radiators are positioned at an angle. Of course, you couldn't put them vertically because that would take up too much space. So they're at an angle, and that means the air gets trapped at the end of that chamber where the bottom of the chamber and the end of the radiator meet. And that's why most of the airflow is being forced through the end of the radiator, which is why you see all of this airflow going through the bottom part, and the top part is really not being used as much as the bottom part. So if you have enough cooling capacity already, that means you can either make do with a smaller radiator and save some weight, lower your body panels, reduce the drag, and so on. Or if you're struggling with your cooling, that means we can help you optimize the flow towards the radiator, change the ducting, maybe add some baffles to force some air through the top part of the radiator, and so on. So that's really an interesting part as well. And when it comes to downforce and drag reduction, it's really interesting to just analyze individual elements. So one of the key things that is time consuming is to set up a model for CFD. Even so, to simplify, take out the small components. At AirShaper, we can just work directly with non-watertight, as we discussed, which is a model with gaps and holes. We can just accept that. But you also don't need to simplify any geometry. So we will automatically copy the component structure of your file, and that means you can afterwards just click on individual components. If you want to know what the downforce is on a dive plane, for example, you can just click on the dive plane and you can analyze the forces on that component without having to set up the meshing yourself. The meshing, the adaptive mesh refinement during the simulation, it's all done in an automated way. So the only thing you have to do is interpret results and improve your design. And you mentioned the Porsche Taycan at the beginning of the video. So if I go to our videos page, the Porsche Taycan, we did a number of things. We did an explainer video, which showcases how this optimization method works. So if you want to see the details, it's for the geeks out there, which includes me, by the way. If you want to see a more tangible result, you can actually look at the Aptera that we did. But before I go there, so the Porsche Taycan has a really nice set of aero features to reduce the drag. Because it's an electric vehicle, you want to increase the range without having to boost the battery capacity because that's very expensive. So on this car, you can see a number of things. You can see that um, we instrumented this with Tufts to test it afterwards. But if you look at this car, at the bottom, you can see it's all very flat. It's very smooth. So there's a nice upward curve on the front splitter to really guide the air underneath the car. There are air deflectors in front of the wheels there to make sure the air doesn't hit the wheels full on at the front. You can see that the underfloor of the car is really smooth and flat. So all of the bolts and the nuts, they've been made flush or actually sunk into the bodywork. And what you can see is that even the suspension, it's a bit hard to see here, but even the suspension got its own covers to guide the airflow even along the cavity that you normally have around your suspension components. So really a lot of work has been put in there. A nice diffuser at the rear. You'll see air curtains at the front. And you will see on the sides, this is the air curtain. So you can see that the air can actually flow through and then gets ejected alongside the wheels there. The wheels themselves are almost like a turbine, really soft shapes to not mix the air too much. And so tremendous amount of information and things to be learned from this car. And then we took it out for a spin. Luckily, Porsche said, yes, here are the keys, go for it. So we instrumented the car with a lot of Tufts, which allowed us to actually correlate our CFD simulations with what we see in real life. So you see here that you have a big separation area because of the outwash of the wheel wake, let's say. And we could also see this in real life, which is evidenced by these small tufts moving up and down. So in a bit, you'll see them moving. So you see that these ones, they're all moving nervously because they're in the turbulent wake here. And the ones at the top here, which are in the green attached flow area, they stay stable. So it's really important to correlate your CFD findings to your real life results. And if we then go to another example of the optimization technique, this one is the Aptera, which is a really nice futuristic car. And they used AirShaper's morphing capabilities to the fullest. So they applied this to various areas: the nose, the top of the car, the belly of the car, the wheel covers, because you have two wheels at the front which are exposed, the rear wheel, and the tail, and so on. And actually, what they did is they first ran a normal simulation, which is the one that you see here, just like the results that we saw. These are real airflow CFD results, by the way. We rendered them in a nice way. So you can see the streamlines here. Afterwards, you'll be able to see the pressure clouds, which is where the wake is still coming from. Not a lot on this car. It's a really low drag coefficient. And then we asked the software in specific areas to optimize the shape. So if I zoom in on this one, for example, here you're going to see that we created a design space around the front wheel cover. And then we asked the software, please reduce the drag. And then in green, you'll be able to see what the morphing magnitude was. So this is real morphing data. So the software was telling us, well, push the rear edge of this wheel cover outward and push the front edge inward. And back then we were very curious to see why this was. And this really opened our eyes, because what the software was telling us is that the airflow around the wheels isn't coming in at a 0 degrees angle of attack. It's coming in under a side angle because the airflow is already being diverted because of the nose of the car. So the software was telling us to design or redesign the wheel covers to align them with the local airflow around the car, which is actually, ironically, to make them point inward a bit. And so we did this. We did this on multiple areas on the car. And the result was that in the end, before we watered it down to match safety and other regulations, we had a 15% drag reduction on the car, which is huge. And then what we did is we had to combine it with safety constraints, aesthetics constraints, cost constraints, and so on. But they were still left with 6% drag reduction on the car, which translates into a massive increase in the range, which is already significant on this car. They're aiming for a 1,000-mile range on their top version. So all of what you see here are actual optimization results, which inspired them to redesign the car. I've been rambling a lot, Jousef.
No,
Which
no,
other questions do you have?
all good. I'm wondering from the simulation point of view, when you do these shape optimization studies, do you define one angle of attack from the airflow, or do you choose different parameters, so to speak, from different angles?
You can choose. So if you have like a limited scope for your aerodynamics study, and I'll close this window straight away.
Yeah.
You would do it for just one angle of attack. It also depends on your timeline, your budget, and so on. But yes, you can have contradictive results between a 0 yaw angle, a 0 degree yaw angle, and a 5 or 10 degree yaw angle. That is correct. So it depends on what your focus is. Do you want to focus on top speed? In that case, because your top speed is so high, the impact of the side wind, which combines into a total vector on your car, is limited because you yourself are going very fast, and then it doesn't make too much sense to look at 5 degrees yaw angle. But if you're looking at an EV, which will be traveling at maybe 70 miles an hour, 100 110 kilometers per hour, then it does make sense to take this into account. Because if you don't, the risk is that you optimize fully for 0 degree. And in that case, you can just make very, very long covers around the wheels, make a very long tail at the car, which is all great if you don't have a side wind. But as soon as you have a side wind, those very long surfaces, which mimic the drop shape, they start to act like barriers or walls if you have a side wind. And then there's really destroys any benefits that you had.
Super interesting. Yeah. I have one question. Like, how do you get started with AirShaper? Let's say you want to fiddle around with the interface, and how much does it actually cost for academics, for professionals?
Yeah,
How do you
yeah,
offer?
good question. So what you can do, there is a pricing page, obviously, and we work with credits. So you pay credits per simulation, and the cost is determined by a number of things. First of all, the accuracy level. So we have a very low resolution, which is just 1 million cells. That's 1 credit per simulation. It's what our hobbyists and students are using. And to answer your question, you can run one of these for free, one per week. The downside is that your results will be made public, and you won't see any force data, like lift and drag are not displayed, but you'll be
Mm.
able to see the flow structure around your object. So if you're a student, you want to just try the platform, you can go for the low resolution one once a week. If you want to go for a decent resolution, which is what you need for a car or for a drone, anything like that, you can go for a regular simulation, which is 10 million cells, and it also costs 10 credits per simulation. And then we have an advanced one, which is what our OEM customers are using. We've got NIO, for example, Morgan Motors, they're using our platform. So the top level one. Now, if you want to get credits, we have three different plans. So we have a discovery plan, which is again for individuals or hobbyists or students who just want to get a bit more insights. You can buy 25 credits for 990 euros. And this one is limited to just basic simulations. So that means you can run 25 of those simulations using your discovery plan. You can also run internal flow simulations, by the way, flow through pipes, valves, and so on.
Mm.
Now, if you're a professional and you want to run regular simulations and you want to include rotating wheels or propellers and so on, which is what we call our pro features, that is part of the professional plan. Same concept, you buy a number of credits, only in this case, you buy 100 credits for 3,000 euros or 2,990, which is actually cheaper per credit than this one. And this one allows you to run regular simulations. So if you spend it all on regular simulations, you can run 10 regular simulations, 10 times 10 credits. What you can also do is run that design advice that I showed you, which is the red and blue color map that indicates how you should morph your design without us morphing it. Then that just doubles the cost. So that's 20 credits for a regular analysis with this suggestion. And the cool thing is you can also use it to get our consultancy. And that's why this plan is actually quite popular with small businesses or people starting a product. It allows you to run maybe 7 regular simulations, which is 70 credits, and then use 3 hours of our consultancy spread out in between to give you insights as to what we're seeing in terms of analysis and how we think you can improve your design. So, a very small scope and low cost option to get started on your project, get some insights, get some feedback, and already get some improvements. And if you then want to go full force in terms of aero optimization, we have the enterprise plan. This one starts at 500 credits for 9,990 euros. So if you would do the math, you would see that this one is 40 euros per credit, this one is 30 euros per credit, and this one is 20 euros per credit. So the cost per credit goes down. This one allows you to run the top level advanced simulation. It allows you to run the morphing simulations, which are 5 times the cost of a base simulation, which includes that Ahmed body or that Aptera that we saw, where we automatically change the shape. And of course, you can run many more simulations. You'll have API access to connect this to your software if you want to run optimizations and so on. So this is the holy grail, let's say, in terms of aerodynamics.
Super cool. Thanks, Walter. We had one question. What method are you using, or what method is AirShaper using behind the scenes? Is
Yes.
it FVM?
Yes, it's finite volume. So we have based our platform on top of OpenFOAM, and that comes with a number of benefits. First of all, OpenFOAM is a very widely used but also accepted library for CFD simulations. So we don't have to argue like, oh, we built our own CFD solver, it's accurate because of this and this and this argument. No, we just use OpenFOAM the way it is with all of its proven accuracy and technology. We run steady state simulations using K Omega SST as a turbulence model. We can also run transient simulations, compressible simulations, and so on demand. Those are not available through the automated platform because they're a bit more challenging to get stable transient and compressible simulations, but they're also available if customers really want. And saying this, I realize I skipped the validation cases, but we have a dedicated page to show how we use OpenFOAM to the max to get the best possible accuracy that we can for a given cost or cell count for a simulation. So we've got a Tesla Model Y case where we got less than 6% delta between wind tunnel test value for drag and our value. We also got laser measurements for total pressure behind the car. Really cool to see the 4 vortices of the roof reappearing in our simulations. But the exact same code without any modification also shows very good correlation. When it comes to drone analysis, this is a drone where we analyze the lift and the drag in function of the angle of attack. And again, very good correlation. We also did propeller analysis together with one of the leading manufacturers where we got wind tunnel test data to compare this to their data. We comply with European regulations, which state that if you want to use CFD to market or to actually bring your solutions to the market to produce add-ons for trucks to reduce the drag, you first have to go through a procedure to prove that your CFD code is accurate enough, and our results are spots in the middle of the error bands that you're allowed to be within. We do internal flow validations, flow through pipes. We have a fighter jet at low speed, and so on.
Excellent. We have another follow-up question. A very informative talk so far. Thank you. How does AirShaper work to model and display surfaces with zero thickness surfaces or scan data? Does it solidify the components automatically or use backside culling?
Well, that's a very interesting question. So in the very early days of AirShaper, we had this interface where during the upload, like this interface, we would have like a warning, and we would highlight the open edges and flash them and say, "Well, please fix this. This is not watertight." But then we saw that this is really, really time consuming and making it impossible for many customers to actually run their project because they don't have the skills or the time to close their model. So instead of closing the model, which you can do with a shrink wrap, for example, or solidify commands and so on, but they're prone to errors, they don't always work, and you can sometimes close gaps which aren't supposed to be closed and the other way around. We decided to just leave the models as they are, which means that, of course, we're not talking about a missing panel. That, of course, would destroy the aerodynamics also virtually. But we're talking about a model where you have a small tolerance where the flow leaks to the inside. Normally, that crashes the simulation. In our case, it doesn't. We will have mesh flowing to the inside of the car, but that's a static pocket of air which is just traveling along with your car because there's no interaction with the outside air apart from this very small miniature gap. Um, Sorry, this represents a computational penalty, of course, because even though the airflow is standing still, you still need to calculate it on the inside. Now we offer fixed pricing, so of course it would be very problematic for us if we would have to calculate the mesh on the inside and spend a lot of money and actually spend more money on the simulation than what we earn with the simulation. But we created our own adaptive mesh refinement. We also made this open source for those who want to check it out. We adaptively refine the mesh during the simulation. So that means if you order a 10 million cell simulation at AirShaper, we'll first run it at 5 million cells, already with the mesh refined using the rules of thumb, like the closer you get if you're close to sharp edges and so on. We let it converge completely, and then we will automatically refine the mesh in those areas where the gradient of pressure and the vorticity and so on are high. We refine the surface, and then we continue with the results from the previous simulation. We map it onto the new simulation. We continue with the 10 million cell mesh, which is much more detailed, with a mesh which is exactly tuned to not just your geometry, but to the flow pattern around your geometry. And that's how we can actually get very precise results, even with a relatively low mesh count in some cases. The cool thing is that because we control this adaptive mesh refinement, we also know that the inside of the car doesn't see much vorticity or pressure gradients, which means automatically our adaptive mesh refinement isn't as aggressive on the inside as it is on the outside, which means the computational penalty or the excess amount of calculations that we need to run is actually quite limited, which in turn allows us to offer fixed pricing even when a model is not watertight. Long
That makes a lot of
explanation
sense.
for a
Yeah,
short
that,
question.
that was a great explanation. Thanks, Walter. A follow-up question from the same person: can the adjoint method be directly combined with restraints like minimum radii, or does it require manual remodeling and verification?
Yeah, we don't have any constraints at the moment for our adjoint methods. So the only constraint that we can apply is the bounding box or the design space that you specify. So this one is a constraint. We will not morph outside this box, or maybe just outside this box because there's some collateral morphing, let's say. But that's the main constraint that we have. So if you want, sometimes you can actually choose an intelligent combination of boxes where you would have a box here, for example, then you would keep this element unboxed, let's say, and then have a second box here to only allow morphing in the right spaces. But we don't have any minimum radius constraints at the moment.
Hmm. Okay, and then last question before we wrap it up. When you do your simulations, do you have to specify the solver, for example, or according to the case in the initial and limit conditions, the solver is chosen directly from the OpenFOAM database without specifying it?
It's always the same solver. First of all, that allows us to actually make the best possible use out of it and make it very robust. And also, you want to be able to have your results comparable between different runs. So, what we would not want is that one simulation gets solver A and another simulation uses solver B, because you then cannot compare the results anymore. So, it's always the simple foam solver, which is the steady state RAND solver with K omega SST as a terminus model,
Mhm.
including the adjoint optimizations. They're also using adjoint K omega SST.
Excellent. First of all, thank you so much, Walter, for the nice deep dive session. I certainly learned a lot, even though I've been in the field for a little bit of time already. I think we'll have follow-up sessions anyway, Walter, right, on different
Yes,
topics. So
right.
maybe 1 or 2 months we'll have the follow-up session. But first of all, thank you so much,
You
and
too.
we'll send any relevant information to all the attendees after the session.
Okay, fantastic. Thanks again. It was a pleasure being part of this, Jousef.
Thank you so much.